The last thing we want to talk about in this chapter is the Heisenberg uncertainty principle, and with that, we're going to start talking about quantum numbers. So back to Niels Bohr, he initially did suggest that electrons existed in orbits. Quantum mechanics treats electrons differently, though. Quantum mechanics says that electrons have both wave-like and particle-like properties. So they behave like waves and like particles, but how can something behave as both? Well, it depends on what it's doing at that moment. If we're trying to monitor it, it does behave as a particle, but it also behaves as a wave. The Heisenberg uncertainty principle tells us that it's impossible to know both position and momentum, how fast something is moving, of a particle simultaneously. The problem is if we can find the momentum of something, then we can't find its position. If we find its position, we can't find its momentum, because if we find one, it changes the course of the other. Mathematically, this is what we get from this. You are not responsible for this math. This is PChem. If you take PChem, you will see it there. You are not responsible in this class. But change in x is your uncertainty. Let me expand this up. I'm sorry. In position. While change in MV is your uncertainty in momentum. We cannot know both at the same time. So the consequence, we have no way of measuring an extremely small object's location without disturbing it and affecting its velocity. If we can determine the position, we will invariably affect its velocity or its momentum. We cannot measure one without affecting the other. So we know that an electron will act like either a wave or a particle, but it cannot behave as both at the exact same time. It will, though, behave as both. That's where this cartoon comes in, Heisenberg's Department of Physics. You're probably here. And this is what happens in chemistry. Specifically, PChem is more often where you look at this stuff. But we can say the probability of the electron is that it's here. So we have what we call probability densities. It's a probability of finding an electron in a specific space and time. Heisenberg uncertainty principle. We cannot assign fixed paths for electrons. The most we can hope to know is the probability of finding an electron in a given region of space. And that's why the Bohr model is not correct. The Bohr model has our nucleus and then our orbits going around. And we can't say for sure the electron's going to exactly orbit that way. We can just say the probability of finding an electron in a specific region of space. Because electrons have wave-like properties, quantum mechanics is also known as wave mechanics. So you may have heard the term wave mechanics. Quantum mechanics is just a mathematical way for us to describe an electron. It's some fancy math that goes together that's, when solved out, predicts the shape of different types of orbitals, and those orbitals are where those electrons will reside. So we get Schrodinger's equation. Again, if you take PChem, you will learn more about Schrodinger, and I will let them explain it there because they're a lot better at this than I am. I can understand it, but I'm not explaining it as difficult for me when it comes to this. I'll tell you guys what you need to know for Gen Chem, but for this part, when it gets into the heavier math, I'm really good at explaining algebra. When it gets into this math, I have a harder time explaining it because I can see it in my own mind, but I can't explain it to others. But Schrodinger's equation, this little h with a hat on top is called your Hamiltonian operator, and psi is your wave function. Basically, what this is doing is it's treating an electron as a wave function. Which is what allows us to describe the probability density, the probability of finding an electron in a specific area of space. If you take PChem, you'll learn about Schrodinger's cat. It's kind of a cool story. Look it up if you'd like to. But basically, it can get kind of morbid there too. So I'll let you decide if you want to look up Schrodinger's cat or not. But it's something that if you've ever taken PChem, you've definitely heard. But again, Schrodinger's equation, I have a hard time saying his name. Schrodinger's equation just tells us that we're going to treat an electron as a wave function, and it's going to help us predict the location of an electron. So treat the electron as a wave function. The wave function itself is known as psi. We have 4 quantum numbers. These quantum numbers are numbers that help us describe the most probable location of finding an electron. Psi squared is the probability density. It's the probability of finding an electron at a specific point or particular point in space. This equation can actually only be solved exactly for hydrogen because hydrogen is just the simplest element we have. But adjustments can be made to factor in for other things such as electron-electron repulsion in atoms that have more than one electron, and we can get useful approximate solutions. But even at this point in time, we can still only solve this equation for hydrogen because the math is just that complex. So it's solving it, and it's giving us what we call these wave functions. So these waves, and this area in between is your probability density. It's the probability of finding an electron inside this space. You notice here I have nodes. These nodes in the functions are where the probability drops to 0. The likelihood of finding an electron there is 0. Does that mean an electron can't be there? Well, it means mathematically it shouldn't be there. Most likely, we'll find the electrons in this space, in this space, in this space, and in this space. So quantum numbers. In the next chapter, I'm going to show you guys how to compare quantum numbers to electron configuration. Electron configuration tells us exactly where the electrons reside. But quantum numbers, when placed in an equation, the quantum numbers give a plot of points for the regions of highest probability of finding an electron. Where are we most likely to actually find a specific electron? They describe the space the electrons occupy in terms of your distance from your nucleus, which is your energy level. This is known as N. The shape, which is your sublevel. This is known as L. The position with respect to the axis, which is known as M sub L. And the direction of spin, which is known as M sub S. Basically, what quantum numbers are doing is acting like an address. They're telling you your state, city, street, and house number. The state being your energy level, N. The city being your sublevel, L. The street being your orbital, position with respect to the axis, M sub L, and your house address being your M sub S. So they're going to just tell us exactly where these electrons reside. Students have a hard time with quantum numbers. It's just a mathematical representation. They like electron configuration better. We're going to do that again in chapter 9. But you do have to understand how quantum numbers correlate back to the electron configuration. Electron configuration is a different way for us to say the exact same thing that quantum numbers are doing. But quantum numbers, all they're doing is they give us a 4 set like this. This tells me energy level 4, sublevel 1, position with respect to the axis, your M sub L is 1 and your M sub S is 1. This tells me the exact electron I'm looking for if I'm talking about a specific element or a specific atom. So a little bit more in depth of what they're doing here. N is called your principal quantum number. It describes the shell of the electron or the energy level. I was talking in the Bohr model how we have your nucleus, and then we have N equals 1, N equals 2, N equals 3. That's this N. That's your energy level. N can be equal to 1, 2, 3, 4, 5, etc., all the way to infinity. It is a positive integer. L is known as your angular momentum quantum number. It describes the shape of the orbital. If L equals 0, you have an s orbital, which is a sphere. We'll talk about the shapes on another slide as well. But if L equals 1, you have a p orbital, which is a dumbbell. If L equals 2, you have a d orbital. There's a few different shapes for d orbitals. And if L equals 3, you have an f orbital, which I cannot draw the f orbitals. At this point in time, we are not going above f orbitals. We could have g. If L equals 4, it would be a g orbital. L equals 5, it would be H, etc. So the beginning of the alphabet, we go by S, P, D, and F. But then once we hit 4, 5, 6, we start following the alphabet down through. M sub L is your magnetic quantum number. It describes the orientation in space of the orbital. M sub L is equal to, so L is equal to 0, 1, 2, 3, 4, all the way up to n minus 1. L cannot be equal to n. It has to be one number less than n. M sub L is equal from anything from negative L through 0 to positive L. The reason is, for P, I have 3 different orbitals for P. I have to be able to describe which one I have. I could have negative 1, 0, or positive 1. D orbitals have 5 shapes. I have negative 2, negative 1, 0, plus 1, and plus 2. Note, for P, I told you that P equals 1. This is negative 1, 0, and 1. I told you for D, L equals 2 for D. Negative 2, negative 1, 0, plus 1, plus 2. Goes from negative L through positive L. And M sub S is your spin of the electron. Is it spin up or is it spin down? Spin up is plus 1/2 and spin down is minus 1/2. Again, we're going to show you how to correlate these back to the electron configuration as well in the very next chapter, but you do have to understand quantum numbers. So if I told you, 3, 2, 1, 1, you should see, okay, n equals 3, my n equals 3 energy level, okay. I've got a 2 here, which means I have a d orbital. My M sub L is equal to 1. And this would be 1/2, I apologize. And my M sub S equals 1/2. So this means I have an electron in my 3rd energy level, d orbital, plus 1 for M sub L, and it's spin up for the electron. And once you get electron configuration, I can tell you exactly the last electron that went into that atom, or that the last electron that went into that orbital, and I can tell you exactly what element this correlates to. So the orbitals. What is the physical meaning of psi? This thing psi we keep talking about. Well, again, psi is just your probability density. It represents the probability of finding an electron in a given volume of space. So when Schrodinger's equation is solved for the lowest energy electron in hydrogen, you get a 1s orbital. 1s orbital, we see, is this sphere-like shape. The probability of finding an electron in this shape is what this equation solves for. Probability density here, meaning that we should find the electron somewhere in here. If we have 1s versus 2s versus 3s, 1s is purple. Under here, we should find your electron in here somewhere. 2s, we got a little bit of probability there, but we've got most of your probability under here. We do have a node in between here, separating all the different energy levels. And 3s. So this math is actually solved to determine where those electrons are. And as a kind of cool video, let's see if I can get this to play through here.
Supporting small businesses and for helping people find jobs. More about all that at the end. Atomic orbitals have long been a source of frustration for me. On the one hand, you have simple cartoon diagrams that make them feel friendly, but which are so varied and vague they don't really convey much beyond the basic idea that atoms have a nucleus and some electrons. Some people try to take the cartoony diagrams and make them feel more random or quantum, which is an improvement, but they're still very much just cartoon stand-ins for the vague idea of atom. On the other hand, you have atomic orbitals depicted as fuzzy clouds or balloons or rainbow donuts, which are definitely more technically accurate or technically inspired, but none of which feel like they give me a sense of what's actually going on. Like, what does this blobby thing have to do with orbiting electrons? Is the electron inside it, or on the surface? Why do some of them have blobs and others donuts? And why are some of the donuts rainbow colored? I want to know what an atom looks like, and I want that picture to actually have something to do with the nitty-gritty reality of atoms, since they are indeed real things. You know, like how a diagram of the solar system is both a totally not-to-scale caricature, and yet also represents the very real idea that the planets all orbit the sun in roughly the same plane, and that some are farther out and some are closer in, and if it's animated, we get to see that the closer planets complete their orbits more often? It's a nice picture, and that's what I want for atoms. A good picture. There are a few things I'd like that picture to get across, some of them because they're important for the physics of atoms, and some of them because they're questions my brain wants answers to. Like, where is the electron? How fast is it going? How much energy does it have? How big is this picture relative to other pictures? Of course, the wave-particle nature of quantum mechanics means some of these ideas, like the electron's position, don't translate exactly from our everyday intuition to the atomic scale. But there is a way of thinking about wave-particle duality where you picture the wave function as a bunch of water, and the particle as a speck of dust in that water. The particle is mostly guided by where the water goes, and the water is guided by the equations that determine how water behaves depending on its circumstances. And if you apply the mathematics of that idea to atomic orbitals, and then render it in 3 dimensions, here's what you get. Isn't it beautiful? Here's another. And another. And another. In fact, I made a bunch of these, and they're all mesmerizing and beautiful, and isn't the ground state of the hydrogen atom just so cute? And aren't the excited states so majestic? There's so much structure and detail in them, I just love it. You can see patterns in the orbitals, and you can get a sense that they actually are orbitals. I mean, something is orbiting. Okay, so I do have to be clear. The dots don't each represent a separate electron. The whole collection represents the wave function of a single electron, and the individual dots represent all the places that electron could be. A higher density of dots means a higher probability of the electron being there. The bigger orbitals are the ones with higher energies, because electrons with more energy are more likely to be far away from the nucleus. The motion of the dots is showing the flow of the wave function, and does correspond to an extent with its actual angular momentum, though they're not electron trajectories. Unless you think Bohmian trajectories are real, in which case they really are electron trajectories. I'll let the philosophers of physics fight that one out. But the point is, these visuals are created by representing actual electron wave functions in a visual language that our brains can understand, that of objects and light and shadows and motion in 3D space. There's actually stuff orbiting, and they're pretty. I hope you like them as much as I do. Oh, one final thing. I 100% get that these are not easy to draw. So if you want a cartoon representation of an atom that's simple but more closely based in atomic physics, here's my proposal. It's based on the orbitals from the p block of the periodic table. One of them has the electron orbiting one way, one in the opposite way, and in the third one the electron is orbiting the same amount, but around some perpendicular direction, and we can't know which is why the dots aren't moving in the middle orbital, and why I've drawn a dotted line and question mark for the sideways circle. And if you want, you can add an electron to each orbital, or 2 electrons, one oriented spin up and one spin down. This is a Minute Physics approved cartoon representation of an atom. But really, the beautiful 3D ones are where my heart is. Thanks to Google for sponsoring this.
I hope that video helps some. I cannot draw them that way. They look beautiful that way. But that's what we're trying to describe with these wave functions. We're trying to describe the electron could exist anywhere in there. And it's moving constantly because it has energy. Everything's moving unless it's at 0 Kelvin, which we're not at 0 Kelvin. We'd all, nothing would exist at that point. But those electrons are constantly moving and they're orbiting in those shapes, in that way, in those wave functions. Those particles are behaving like waves as well. So solving all this, we get these different orbital shapes. You are responsible for being able to draw s, p, and d orbitals and recognize f orbitals. So an s orbital is just a sphere. We see here we've got different examples of s, 1s, 2s, 3s, and so between each one we've got this node. The node in between here, and we saw those in the video as well, is where the likelihood of finding an electron is very, very slim. Your nucleus is in the very center, and then we have the nodes. So, for s orbitals, n, your energy level, can equal 1, 2, 3, all the way to infinity. L, these are your quantum numbers, L is equal to 0. No exceptions. If your L is equal to 0, you have an s orbital. M sub L equal to 0. No exceptions. And m sub s can be equal to plus or minus 1/2 for every type of orbital. P orbitals, we have what we call the dumbbells. Some people call them bow ties, figure eights. I call them dumbbells. They're shaped like this, and like this. We have 3 different shapes: PX, PY, and PZ. Notice it's kind of hard to see here the PY. It's supposed to be going like behind the board and in front of the board. This is what they look like when they're all combined together. This is where we get that -1, 0, and +1, depending on which order you draw them in for your m sub l values. For P, you can have an n equal to 2, 3, 4, all the way to infinity. Note, n cannot equal 1 for P block. It does not start until 2. It'll make more sense when you see the periodic table, but for right now, you just need to know that n equals 2, 3, 4, all the way up to infinity. L equals 1, and m sub l will be equal to -1, 0, or +1. So most often what we do is we write them in here for the px, py, and pz orbitals. We could write this as, say, n equals 2, L equals 1, but m sub l will be equal to -1. N equals 2, L equals 1, m sub l will be equal to 0. N equals 2, L equals 1, but m sub l can be equal to +1. Now, within here, I could have m sub s equal to plus or minus 1/2, m sub s equal to plus or minus 1/2, and m sub s equal to plus or minus 1/2. Each one of those can be 1 electron. So I can have an electron here, electron here, electron here, electron here, electron here, electron here. It's like you can have 2 people that have the exact same house, but they have to sleep in different beds. It's basically what's telling me. The electrons have to be paired opposite. We call this your spin. Spin up. And spin down. The electrons have to be opposite spin. Or they repel each other. No 2 electrons can have the same 4 quantum numbers. We also have your d orbitals. For d orbitals, n can equal 3, 4, 5, all the way to infinity. But L always equals 2, no exceptions. So we see we have dyz. We're going to call that m sub l equals -2. dxy, m sub l equals -1. dxz, m sub l equals 0. dx squared minus y squared, m sub l equals +1. dz squared, m sub l equals +2. It's hard to see on here, but where you have the dyz, dxy, and dxz, your electron density is between the axes. So here, we are between the y and z axes. Here, we're between the x and z axes. Here, I'm between, or here, it's up here. I'm between the x and y axes. Now, where it says x squared minus y squared and dz squared, this is along the y-axis and along the x-axis. So when you've got the square in here, it's because they're along that axis. And dz squared means that it's along the z-axis. And this forms what we call the donut shape. And again, so m sub l can equal -2, -1, 0, +1 or +2. And m sub s can be plus or minus 1/2. So spin up or spin down. The last set of orbitals are the f orbitals. There are 7 f orbitals. So let me back up just a second. I forgot to specify that. S orbitals, L equals 0, m sub L equals 1. We have one shape for s orbitals. One shape that holds 2 electrons. Each specific shape holds 2 electrons. So s orbitals hold 2 electrons each. P orbitals, I have 3 shapes. Each shape holds 2 electrons, so overall 6 electrons can be held in my p orbitals. My d orbitals, I have 5 shapes. Each shape, it's each subshell, can hold 2 electrons, so overall 10 electrons can be held in my d orbitals. And F, I have 7 shapes, which is 7 subshells, which means 14 electrons can be held in your F orbital under one specific energy level. So if I have n equals 4, L equals 3, which is your F orbitals, this consists of 14 different electrons. You are not responsible for drawing these. You're not responsible for knowing all their names. You are responsible for recognizing them, and you're responsible for knowing that n equals 4. If it's an F orbital, it has to be n equals 4 or higher. We cannot have F orbitals until we're the n equals 4 energy level. You have to know that L equals 3 is an F orbital. You have to know that m sub L can be equal to -3, -2, -1, 0, +1, +2, or +3. And then m sub S, of course, as always, equal to plus or minus 1/2. So you could say -3, -2, -1, 0, +1, +2, and +3. And remember, each one of these can hold 2 electrons. So overall, 14 electrons being held. So that is the end of the Chapter 8 lecture. Here is your additional practice, which is recorded in a different video. Please work a lot of these problems. Please look through the additional practice and see where you're having deficiencies and work some extra problems in there. Good luck.